Good afternoon, everybody, and welcome to the second half of the fourth day of the 6-day workshop. So this session will be conducted by Dr. Abhishek Datta he's from Iztek, Turkey, Izmir Institute of Technology, and he'll be talking about conjugate heat transfer in an enclosed domain. So you can have an ice-breaking session with Dr. Datta.
So hello everyone. So I just wanted to know that if you have any, I don't know if you have any prior knowledge of conjugated heat transfer. Have you studied something in your sessions, in the university? So maybe I can ask the one who says yes. What have you learned in the basic thing? What is about conjugated heat transfer? I mean, of course, it is very basic thing. It's not nothing super science, but what is the main reason that we study conjugated heat transfer? Maybe that is more clear. And please try to avoid looking at the internet for answering questions. Because that's the problem of online teaching these days or online seminar. Just uh, tell from your mind actually what do you think? What is a necessity for this?
Yeah, actually, as per my experience, the when someone say conjugate heat transfer, it's basically how the air is going to interact with the heating surface, the physics behind those things.
Yeah, the physics behind those things is definitely important. I agree with you. That is actually the most important thing. But
Mhm.
also when we talk about conjugated, there is this term conjugated. This conjugated term is the most critical one, and that
Yes.
means that there is a combination of more than one heating mode of heating. Right. This is the
Yeah.
the main reason, and how we interact with this mode. So you guys are young students, and I suggest you that uh, look into this because there is still some knowledge gap on these areas. There's still some knowledge gap. A lot of research gap is there in this conjugated heat transfer phenomenon. Although it is a very important one, I'll show you with one example in my slides in my presentation about this. It is just one. I mean, I myself have started working very recently on conjugated, just 7 months, I think 6 7 months. So I'm not an expert in the field at all. In any case, in any level, and hence I'm always looking things at a very different perspective all the time, and I see that a lot of research gaps are there and things like that. So we will not have too much time to discuss about the research gaps. As you know, the session is also limited, and my knowledge is also limited. To be very honest with you all, but at least I'll show you some ideas. I'll show you some pointers that could be your could drive your thinking actually. So that would be interesting. So yeah, it is what you said is very important. The physics is very important. You have to first understand the physics for any numerical problem. We are actually in fact solving physics problem. This is the whole point of heat transfer, mass transfer, fluid mechanics, or rather transport phenomena in general is actually physics problems. These are actually physics problems, and there is some chemistry that adds up into that when we do some chemical reactions. Otherwise it's purely advanced physics problems. So yeah, that's definitely the case. So just to also know you all, are you all from IIT Bombay or you are from other institutes of India?
IIT Kharagpur.
Okay, nice. So you are from different IITs and different institutes of India, and you have registered for this the whole session. So how have you been experiencing so far? And are you all open form enthusiasts? I believe that you're gonna take up open form, right? In my presentation, there is no open form, but we have a demonstration session. So the whole point is again showing something in a very standardized software, and then eventually sending it to open form. So you're all going to be working in open form in the near future, or what's your plan? I mean, what is the motivation for you to join these sessions? I see that you're working on learning OpenFOAM from scratch. Nikita, excellent, very good. Sharifuzaman says that both OpenFOAM Python. Okay, be aware that Python is can be added as an additional tool, right? So for all the processing, for all the analysis, you can add Python to the OpenFOAM. So that is also very good, of course. use it for research purpose by comparing CFD output with practical or other calculation? Yes, definitely. Be aware that CFD is not always the ultimate answer, because CFD is all about numerical research. I personally try to work on analytical solutions as well, because analytical solutions are the result ultima, as they say. But the problem is that analytical solutions are very limited. So if you can at least find out uh, approximate analytical solutions, I think one of my or two of my slides have that. You should be able to also encourage yourself to focus on this analytical, approximate analytical, if not accurate analytical or correct analytical, at least approximate analytical solutions. These are very important because often you get nice pictures, nice results, but are those results correct? And how much your practical results can give the correct solution? That's also, I mean, you have all started, and I see, with a lot of enthusiasm, which is very good, by the way. But be aware that the experimental works always have a limitation. Means you cannot bring the reality, in your lab or in your pilot scale, whatever you're doing. So there will be always a gap between CFD or numerical work and experimental work. So that big gap is where you bridge it through an analytical solution. So that's basically the idea. You bridge the gap of experimental and the numerical one with the analytical, or at least approximate analytical. That's basically the goal, actually. So I always encourage, even my students, I encourage to use at least analytical or approximate analytical procedures to ensure that the answer is the CFD answer or the numerical answer is correct. So, guys, hello everyone again once more. Welcome to the presentation of understanding conjugated heat transfer. So I wrote this word understanding because I'm also in the same process of understanding this, and I am not an expert in this field. Take years to be an expert on this field, of course. So I come from the İzmir Institute of Technology. As you can see, it's written in Turkish, but doesn't matter. İzmir Institute of Technology. I'm an associate professor in the Department of Chemical Engineering. Also, I have associated affiliations with the Department of Energy Engineering and Computational Science and Engineering as well. We will be talking about conjugated heat transfer in the aspect of some fundamentals, some not so fundamentals, and the progresses and the challenges. These are, of course, my challenges, and I assume that this will also be your challenges as well if you take on this topic in the near future with your research and developmental activities. Okay. So as usual, the typical drill of any presentation is to let you know what I'm going to present. And this presentation is divided into some topics or some aspects here. We are going through the linear and the non-linear aspects of heat transfer. We'll try to see what they are. And then we'll talk about the physics of conjugated heat transfer. Then some, as I said, some with a bracket, which means that there are no complete list of analytical solutions for different aspects of conjugated heat transfer. So there are only some solutions that are available. And so this will be also discussed with you. And the example case of one practical application of conjugated heat transfer, I found it very easily explainable paper, and which is very important. When you are starting with something which is more complicated as this kind of topic, it is always best to start with something very easy rather than start with something very complicated and wasting your time and energy trying to understand that topic. Then we'll talk about discuss about the recent progresses about the heat transfer and some challenges which are in CHT or conjugated heat transfer. Okay. So here, as you see, the whole story of heat transfer is actually not a very new topic. It was something it was something that bothered people long back. Almost 200 years ago, Joseph Fourier, he actually gave this heat transfer theory. We all know by now what is it, which is called the Fourier's law. And this came into existence along with the Biot's, John Baptiste Biot. He was a pioneer as well, who did some experiments to understand the lay the foundation of the thermal conductivity. So this is when we said about heat transfer, we include the process of heat conduction. We also include the process of heat convection, and also we include the process of heat radiation. Be aware that heat transfer is not just only heat conduction, but I'm just informing you this just to let you know that these are some important people. These are some so-called gurus of these of these topics, and we need to keep in mind about them. So again, heat transfer is basically a physical problem, as one of you, Paritosh, also rightly mentioned. It's a physical problem, but also it has its basis in thermodynamics, and it basically explains how the thermal energy. So that's very important. How the thermal energy is transmitted. It is all about the energy. The energy is in the form of the heat. So it's a heat energy which is transmitted from one material to the other, either through another material or through no material. So it could be a medium which can be completely air. So that is the whole point about it. Okay. So the basis of, again, this heat transfer can also be regarded to Rudolf Peierls and David Bohm, who gave this phonon theory. I guess if you don't know, you can Google it later after my presentation. What is phonon theory? I think I may have one slide later I can show you also. It's a very interesting point, which basically the phonon theory is not a new thing as well, but they are basically it's a quantum physics topic. It's a way the particles are basically used to the particles are this phonon theory is actually the way in which to model the so-called lattice vibrations. That's basically what is mentioned here, the lattice vibration, and this phonon is nothing but a packet of discrete energy, and basically when it travels, the phonons are basically vibrating, and once it vibrates, it's the energy is transmitted from one to the other. So it's a keep in mind that these phonons can interact with particles. It can interact with particles which are that are associated with other quantum fields, such as photons. So do not confuse phonon with photon. Photon is different, and the photons are nothing but the quantums of the electromagnetic field. So this is the very basic background of or the basic understanding from where this heat energy, the whole topic of heat energy, came about. And it is important while we discuss this thing that we understand that the basis is basically the phonon theory. So now we come to the very standard definitions and these mathematical expressions all about the two aspects of heat transfer. I mentioned there is a linear heat transfer. I don't know if your teachers have told you this in your classes already, or you might have also seen from the books and so on. So heat transfer is basically that can be divided into two aspects. One is the linear heat transfer and the non-linear heat transfer. So let us first look into what is the linear heat transfer. We have not got into the conjugated heat transfer yet. We are only looking at the linear heat transfer as of now. So the linear heat transfer is based on, again, Fourier, as I just mentioned a few seconds ago. Fourier's law of heat conduction, which states that the heat flux, in this case the Q, is directly proportional to the negative of the temperature gradient. The temperature gradient can be expressed in terms of dt over dx. If it is in one dimension, if it is in multiple dimension, you just add y, z, and so on. So while this is directly proportional, there is also, when we bring it in an equation format, you already know by now that the proportionality constant is nothing but in this case a K, and that can be attributed to the thermal conductivity of the material itself that we are talking of. So where we are doing the conduction, where we are seeing the conduction, the thermal conductivity is referring to that. So in terms of mathematical expression, this is basically Q equals minus K, since I said it's negative, minus K dt over dx. You can ask yourself why it is negative. It's a very important question as well. Why it is negative? Why the heat transfer is negatively proportional to the temperature gradient? This is something that you should be clear from your side as well, because these are very fundamental and very basics. So mathematically, heat flux is proportional, negatively, of course. The common isotropic and inhomogeneous materials under normal conditions, and it is valid within a specified temperature range. This is very important, that it is valid within a specified temperature range. Okay, these are the three important aspects of this equation, the linear heat transfer, and you can already see the linearity. You can see that it's a more or less a linear relation, that it can explain the, or it can give the relation with the temperature gradient and thermal conductivity of the material. Now then, what is nonlinear? Obviously, when the linear comes, you come up with the second question: what is nonlinear? And nonlinear is, as I have mentioned here, it is the mode of heat conduction characterized by a deviation from the linear relation between the heat transfer and the temperature gradient. So that is very interesting now. So what I'm saying here is that the heat transfer is no longer a linear relation, no longer can be expressed by a linear relation, but it is typically expressed as a non-linear relation, whereby now there are two important terms that comes into the picture. One is this time variation, the temporal variation, as well as this hyperbolic term. So these two terms bring about the nonlinearity. That's the mathematical aspect, of course. So in case of nonlinear heat transfer, the relationship between the heat transfer, the heat flux, the Q, which I've already seen in the last slide, and the temperature gradient and the other relevant parameters, little bit more complex, and they are not proportional to each other directly, and they are not also having a direct time dependent behavior. So in this situation, you may ask yourself that where is this nonlinear relation happens? Where is this nonlinear relation can occur? It's a very important question. So these nonlinearities are actually the most common, to be honest, the most common one. For example, when you have, I don't know if you have heard about the topic called thermal runaway. Maybe you have not yet heard about it. Thermal runaway are the situations where something disaster is going to happen in a company, in a factory, in a chemical factory, or in a factory where there is some energy calculations, energy production involved, things like that. So it's an energetic process. Let's put it like that in a more easier way. In an industrial setting, thermal runaways are very common, actually, very common. And so these nonlinearities can lead to phenomena. These nonlinearities, that the nonlinearity that I just mentioned to you here, it can lead to phenomena where there's rapid temperature change can happen. And in this case, this rapid temperature change is nothing but a thermal runaway, where suddenly temperature went very high. For example, the huge accident that happened in the Bhopal gas tragedy. We all remember that very well. We should not forget what happened in such a tragedy, where there was an extreme thermal runaway, and of course the radiation. Radiation was also a very danger, and it killed a lot of people for many years after that situation happened. Anyways, so this nonlinearity can lead to phenomena such as thermal runaway. It can lead to temperature dependent material properties and transient effects that typically that cannot be captured by linear effects. So this is a linear way. So keep in mind that nonlinearity is an equally important aspect of linear heat transfer, and this nonlinearity is actually more relevant for the industrial point of view. So if I want to give you a summary, if I want to summarize everything, I would say that linear heat transfer assumes, you may say, a linear behavior in the governing equation and the material properties. Let's put it like that. While the nonlinear heat transfer basically takes into account the deviations from this temperature that happens due to temperature dependent properties, boundary conditions, phase change, or the radiation effects, which I just mentioned with the Bhopal gas tragedy. So these are important factors to realize that there is a non-linearity aspect of the heat transfer, and not always do you get a linear relation. So having said this, we are now going directly deep into or at least going into the understanding of, as I said, it's not an in-depth study, but an understanding. So we are now going into the conjugated heat transfer, trying to understand now what exactly this means. So we come to the definition. The first thing will be to understand what the conjugated heat transfer is. And the conjugated heat transfer involves the simultaneous simultaneous, so one along with the other, simultaneous consideration of heat conduction in solids and heat convection in adjacent fluids. This is one. It could also include radiation. I didn't mention here, but it could also include radiation as well, very much, of course. So this convection and conduction, the simultaneous consideration is an example, or is a good definition, or is a decent definition, not a good, a decent definition of conjugated heat transfer. Where does it occur? This occurs in lots of industrial practices, typically where there are some solid structures that are involved, solid structures. In this case, walls, the walls of the structure, fins. When I use the word fins, probably you might have already started understanding that I hint about heat exchanger, because there is a fins. The fins are involved there. And these solid structures, when it interacts with the surrounding fluids, you have a combination of conduction and convection. Keep in mind that radiation is also a part of conjugated heat transfer as well, which I didn't mention here, but I have an example. I have a case study, and I can tell you the radiation factor there as well. Okay, so for the heat conduction in solids, so as I said, it is a simultaneous consideration of heat conduction in solids and heat convection in adjacent fluids. Let's look first into the heat conduction in the solids. We already know by now that was the heat conduction equation that you have seen from the previous case with the Fourier's law. It governs how heat is transferred through the solid material, and of course the multiple parameters that are involved in this heat conduction are basically conductivity. I've listed down here also conductivity. There it's a density, specific heat, a temperature distribution, and the time distribution. Temporal variation is the time, temperature variation, and the temperature distribution within the solid. So these are the parameters that are involved in this mathematical expression of heat conduction in the solid. Now, this is the solid part. This is a conduction part of the solids. Now, as I said to you, that conjugated heat transfer involves both heat conduction and heat convection. So we also need to see what is happening in the heat convection as well. So the heat convection, as you know, or you may not know, is basically based on the very useful equations of Navier-Stokes. So Navier-Stokes are the flow equations that are also, since flow is an energy, heat is also a sort of energy. I've already explained to you in the couple of minutes ago. So it is described by the heat convection in fluid is described by the heat convection equation, which is the Navier-Stokes equation. And basically this heat convection is the way how the heat is being carried by the moving fluid. This fluid could be air, typically that is the case, air, or it could be, for a heat exchanger, it could be a heat exchanger fluid. It could be a water, it could be something else, a fluid that basically has a good property to carry the heat, because the whole point is to be able to carry the heat from one point or one source to the other. So that's part of the convection, right? So this is the expression, and this expression basically gives the relation between the thermal conductivity of the fluid with the temperature distribution and the velocity vector. So you see here that there is this additional term, the velocity vector. I have not used the vectorial expression, but it's okay, doesn't matter. So this vectorial expression of this velocity vector is actually where the governing is where the Navier-Stokes equation is all about. So Navier-Stokes equation comes into play when you have a fluid velocity vector in the convection equation. So all good until now. We have heat conduction in solids and heat convection in fluids, but there is a little issue. The issue is that there is now a jump. There is a jump between the solid and the fluid, right? That's the critical thing. We talked about two separate blocks. Okay, we talked about two separate blocks. These two separate blocks are basically about the solid and the fluid itself, but how to connect them, how to ensure that the heat is going from the solid to the fluid. That is the main thing about the conjugated heat transfer. So conjugated heat transfer in this case is important to realize, as different from the other aspects of heat transfer, is that you are now considering the transfer of the fluid by assuming that the temperature at the interface, at the interface, at the interface of what? At the interface between the solid and the fluid, that there is a continuity condition. This continuity condition is this. So this is very important, that the temperature at the surface of the solid surface, that is at the interface. So at the interface, temperature of the solid will be or has to be equal to the temperature of the fluid. This is a very important condition, without which the interface interaction, this is a very important interface interaction condition, without which the conjugated heat transfer will not work. So this means that the mathematical representation of the heat flux, you may ask now yourself, there are some messages coming. Why there is no CP in the convective? Yeah, okay, I get your part, but yeah, it's difficult. I cannot see the chat, and when you're writing, so the CP, I assume the CP inside the lumped parameter. So you're right. We can put, okay, absolutely, it's okay. You can put the CP part as well. It is a lumped parameter inside, so with the density, I didn't bother about that. You're right. So you know my answer now. Of course, to be very explicit, we are in the research, we always lump some parameters, and in that case, I have lumped the parameter, but you are right. If you put it in explicit form, indeed. So coming back to this interface. So this the interface which I just mentioned about is the which accounts for the thermal interaction between the solid and the fluid domains. What does this actually does? This mathematically, this basically represents the heat flux. The heat flux, it remains smooth and consistent as it moves from the solid to the fluid domain. So this is very important. So this heat flux, if there is a jump in the heat flux, then your solution will never come correct. Okay, this is very, very important. And that's why using open source tools are very important, where you can actually see what is happening and you can understand what is going on. So this continuity assumption is vital, very important for accurately modeling and simulating the heat transfer between the solids and the fluids. Most of the time, the mistakes comes because of this wrong interaction, wrong assumption of the interaction that is being taken. So we engineers, or you guys, when you will become engineer, you can use this approach to predict the temperature distribution, heat flux, and other critical thermal parameters relevant to design optimization, such as durability and energy efficiency, using this interface interaction. Very, very important point, as I told you. Keep that in mind, that this interface interaction is a very, very critical parameter for handling a correct way of conjugated heat transfer. It's just an example of a conjugated heat transfer I just mentioned you, convection and conduction. There is much more to that. There is radiation involved. So now, since I have talked about conduction and convection, I'll try to show you some examples of analytical solutions of this conjugated heat transfer. Okay, so these are some available examples or available analytical solutions, and I have been telling to you that any numerical study or no numerical study is complete without an approach of analytical or at least pseudo-analytical solution. So we have, unfortunately, because of the limitations of the mathematics itself, we cannot go for they're very challenging, that's very sure. Analytical solutions are very challenging, and that's why this kind of analytical solutions are limited to very simplified geometry and simplified boundary condition. Of course, myself with my colleague, we are pushing the limit of this analytical boundary, and we are trying to get even solutions that do not have the standard geometry and standard shape, and the boundary condition. We are trying to push that, but it is not easy, because there is a big gap for us as an engineer, because that is where mathematics people are strong at, but mathematical people do not know the knowledge of engineering, so they cannot understand where the analytical solution would be added and for what implication. Anyways, so I collaborate with mathematicians from Turkey, and of course with Belgium. So try to get some mathematical analytical solutions are very important. Let us now focus a little bit on this analytical solution. This is an analytical solution of a heat conduction with convection for a thin plate. It's a thin plate conduction. As you can see here, that we use the what we do here is that we use the for any thin plate conduction, we start with the using of the Fourier's law. That is the basic for everything, with the heat conduction along with the convective boundary condition at the surface of the plate. So in that case, we consider a thin plate of thickness L exposed to a fluid temperature of T ambient with a heat transfer coefficient of H on one side, and the other side, of course, is insulated. You understand, otherwise the solution is not proper yet. So the temperature distribution for this plate, this analytical solution does exist, and the temperature distribution within the plate, including the both conduction and convection factors, is actually the solution that is mentioned here. So this equation, that is T ambient plus T0 minus T ambient exponential of minus Hx over K, where X is the distance, H is the heat transfer coefficient, K is the thermal conductivity. You know all these things. So you have the expression. This analytical expression is actually the expression at a distance X from the insulated boundary. From the insulated boundary, this is the expression that you can get. This equation represents the temperature distribution within the thin plate with convection, of course, and it shows how the temperature varies with distance from the surface onto the plate, taking into account both the conduction within the plate and convection at the convective heat transfer, the convection at the surface of the plate. Okay, so this is a good analytical solution that I can share with you. This analytical solution is quite useful. We use this kind of analytical solutions for designing certain engineering problems. For certain design considerations, we use such conditions where we are encountering such similar conditions, of convection and conduction. We can use this as a good example of an analytical solution. Coming to another example. This example is about an semi-infinite solid. By the way, I want to be clear with you. So, do you understand do you know what a semi-infinite solid is? Any one of you, do you know what a semi-infinite solid is? What exactly is a semi-infinite? Because before I keep on talking all these things, it's better to know what is the basic thing here. So, we are talking about the transient heat conduction in a semi-infinite solid with convection. So what is a semi-infinite? What do you mean by a semi-infinite solid? You must have done your heat transfer, so you should be knowing this. Can someone write it or talk if you can? Semi-infinite is basically, it has a single surface, and as you have mentioned here, that it extends in all directions except one. So that's the little mistake of me too. You have mentioned a single surface extends in single plane surface, indeed extends in all directions. That's infinite. So semi-infinite is extending to infinity in all directions except one. So what happens is that if there is a kind of like a sudden change that is imposed to the surface, you will have this transient one-dimensional conduction that will happen within the solid. That's all. So good. I see that you're all very active and very good.
Sir, I have a question. So for this semi-infinite, so as we can see, temperature is a function of one direction only. So a
Right.
semi-infinite solid could be a body which has only one dimension. Suppose infinite length rod.
Infinite length rod. Yeah. That's the case. Indeed. Yes, absolutely.
So then
that's,
how could it be plane? 2D.
Sorry, no, it's a conceptual plane. It's a conceptual plane. As I told you, it has a single plane surface, which is a conceptual. In a 2D, it's a single plane surface. But if you consider in the 3D aspect, of course, it has of course, these are conceptual things. Semi-infinite solid does not exist in real life, as you know. So these are just some basic parameters to understand the concept of the analytical solution. As you have correctly guessed, semi-infinite solid is a conceptual solid, which is kind of like a single plane surface extending to infinity in all directions except one. That's basically the idea. And if there is a sudden change that is happening to this one of these surfaces, there is the one-dimensional conduction that will happen. So it's a very, very, very unrealistic reality, by the way. So let's put it like that. So if you consider the semi-infinite, let's say an example of the semi-infinite solid. we have the analytical solution can be derived. In this case, the analytical solution needs to be used the Laplace transform. I guess you have already done your Laplace transforms in your mathematics, basic mathematics. And if you remember this one-dimensional heat conduction equation in a semi-infinite solid, look at the book of Impropera. You will find there, I'm sure, with this convective boundary condition at x equals 0. You have this dou squared t over dou x square. I'm just telling by my mind, so I may be a little bit mistake here, but it's dou squared t over dou x square, I think, equals to 1 over alpha, and 1 over alpha is multiplied by dou t over dou x, right? Dou t over dou t, sorry, dou capital T over dou small t. So this is the main equation, and this equation, of course, you can solve it using this Laplace transform. Now, coming back to the expression that I've written here, if you have at time t equals 0, the surface of the solid is exposed to this temperature ambient with a heat transfer coefficient h, and there is a temperature distribution that is happening between this the temperature distribution that is happening between the 0 and ambient temperature, of course, for the direction, for the length of the semi-infinite solid. We can express this condition by reading out by using this equation, and this expression is very interesting because it has an error function as well. So it uses, as you see, it is not a direct equation, it's a little bit complex equation which has a complementary error function. And this temp equation that you see here, it relates the distance from the surface, the thermal diffusivity of the solid material, but also it accounts for both the transient behavior of the conduction and the convective behavior. So this paper that I've mentioned here, this paper basically discusses about that. So you can also have a look at this paper in later. I have just one more analytical solution. This is the one that I have done with my students here a couple of months ago. Here, this is a very complex problem, by the way, and I told you I'm a big fan of these analytical solutions. So here, what we have done is that we have used because of our problem that we had at hand, we use this concept of this long cylinder approach, where we assume that the convective heat transfer is a constant. Initial temperature distribution is uniform along the radial direction. Expression is mentioned here. And we solve this actually using this kind of so-called Bessel functions. You already are aware of, you might be aware of Bessel function. This is a very challenging problem, by the way. This work has not been published yet. This was a very challenging problem, and my student actually, he solved the problem by this analytical solution by use the method of separation of variables. I don't know whether you are aware of this. This is a mathematical technique. She is a mathematician. So she uses the separation of variables technique in order to solve this resulting ODEs, which leads to this kind of complex equation. So this is a new thing that we could give to the scientific community for the heat transfer. This work has not yet been published because we are still working further on this area. Anyways, so as we see here, that this complex equation is only or can be only solved when we have a pseudo-analytical. So this is not an exact analytical solution compared for the kind of geometry that we're looking for, but we used a similarity of long cylinder approach, and by that we had this expression where we could use as a kind of like with using appropriate boundary conditions, we could use this work. Okay, so it's a kind of like a let's say a mathematical simplification to the analytical solution, to the real analytical solution that we could have expected. Okay, so now having said all these stories about analytical solutions and trying to encourage you all to, I sincerely encourage you all to focus on analytical solutions. So let's go to one of the numerical example of this conjugated heat transfer in solar cooker. I took this example, guys, because first of all, it's a very interesting thing for us, because this example can be a very practical thing. I think more and more solar cookers are getting popular in our countries, for example, in India, also in Turkey, as I see here, because of the abundant sun. And here, just one interesting paper I want to discuss with you all. Very, very interesting paper. The paper was actually, you can search the DOI. It's a recently published paper, also from Indian authors, from Abhishek Sarangi and et al. They are from, I see here, I've written down a note, from the Odisha Institute of University of Technology and Research, Bhubaneswar, and they have collaborated with an Egyptian professor from Mansoura University. It's a very interesting problem, an interesting solution that they have done, because this solar cooker is a very common thing also in countries like, the Maghreb region, Algeria, Morocco, Egypt, Libya. Because of the sun, their solar cooker are getting more and more popular, and also the off-grid, the way of off-grid life is getting popular. So for this paper, I go a little bit quickly now. So there has been a lot of papers on solar cooker, but this paper I found, this is not my paper, just to be clear. This is Abhishek Sarangi's paper. So I really like this paper, and I wanted to focus on this. So this paper, they worked on convective and radiative heat transfer. So it's not just convective anymore, conductive, not conductive, but convective and radiative heat transfer in the cooker cavity. The cooker cavity is basically this one. If you can see here, the cooker cavity is this one. And they wanted to say what would be the optimal form, size, and shape of the solar cooker to gain the maximal heat transfer, obviously for the cooking purpose. Okay. So in this, I'm gonna go a little bit quicker now. What they have done is that they considered the heat loss caused by the radiation and laminar natural convection in a solar cooker that has a rectangular and trapezoidal cavity. So that's basically this one, rectangular and trapezoidal. They considered 4 cases. I'll come to that in the next slides. 2 possibilities were considered for the top wall. They considered cold wall and losses from the wind-induced convection and radiation. So wind-induced convection and radiation is one loss, and the cold wall is another possibility. Okay, 2 possibilities for the top wall. Top wall is the most critical, as you understand. This is the top wall. This is the most critical one. The parameters of the heat loss in various depth cavities, and also they did a nice parametric study, a very clean and easy paper to understand their work. And for me, it was very nice, very easily understandable. They also did the cavities flow pattern, isotherms. Now, I have some pictures of that, but this is the DOI. You can just note it down. You can print screen it, and you can look at yourself this paper in much more detail than what I'm presenting now. So what they have done here is there is an algorithm. They developed this, or they proposed this algorithm. They proposed the standard way of working, starting with the computational geometry, and then these 4 cases, 1 and 3. Case 1 and 3. They are both rectangular and trapezoidal, and of course, with the top wall boundary condition was isothermal, as I told you before. And the second and the fourth case are this one, where the air is non-participating, and they have the external heat transfer that is happening here. Okay, so these are the 4 cases that basically they put into the model, and they use, of course, they use ANSYS here. They don't use OpenFOAM. Would be nice now if you guys can actually reproduce these results in the future with OpenFOAM. They use the solver. I think the solver was probably the Simplex algorithm. And on this, they basically did the grid independent study, verification, and of course, finally, the nice parametric study and the results and the conclusion. Very, very nice and very easy paper for any first timer in conjugated heat transfer to understand. Okay, not very complicated at all. So I have
What is
already
parametric study?
Parametric study means that, for example, if you have certain parameters like length, height, you're very varying through the. I mean, this is a phase of the design optimization. So you do certain changes in the length, you do certain changes in the height, you do certain changes in the shape, for example, aspect ratio. If you do all these changes, you have to do multiple simulations of different values of that. You understand me, right? So that is basically a parametric study. It's a kind of like
optimization.
Yeah, optimization at the end, but you do what is called as let me remember the word, design of experiment. Have you heard of this word? Design of experiment, DOE. Let me write.
Yes, sir.
DOE.
Yes, sir. Yes, sir. Yes, sir.
Okay, very good. So design of experiment is actually basically the parametric studies. We always do these parametric studies before you actually finalize a design. Before you finalize a design, you actually do this parametric studies, and of course the sensitivity studies. That's
So in
related.
design of experiment, we have to do some sort of physical experiment or simulation based
Yeah, that is a
thing.
good point. In the design of experiments, ideally you should do physical experiments, ideally. But as you
Hmm.
know, these physical experiments are very expensive. So what we do is that we go in silico. We go to the computer, we reduce our design scope. You understand me, right? We reduce. So let's say we have 100 parameters in the problem. Let's assume. May not be the case, but let's assume. Now these 100 parameters or 100 changes of these multiple values will take enormous money to do physically. So what we do is that we import this problem to the CFD software. In this case, the open form, which will be open form for you guys. For me, I still work with ANSYS. So for me, ANSYS, or for example, Phoenix. And then I try to get the results, and these results for each of the, so there is a parameter, that let's say parameter of length, and I have to vary between 1 to 5 centimeter. So for an increment of 1 centimeter each, I will have to design my experiment based on this length scale, which is changing from 1 to 5. Am I clear, actually? Are you able to understand?
Yes, sir. So can't we use a non-dimensional parameter to obtain the results?
Yes, sir.
No. You can't use that. No, non-dimensional parameter is only, good question. Non-dimensional parameter is only done when you have optimized. But before optimization, your non-dimensional parameter will not give the correct result because you do not know it. You have to make your non-dimensional parameters, right? You have to have your non-dimensional parameters, but before you design something, it's a completely new system, for example, then you have to go through this design of experiments. Once you have optimized, then you have to do the scaling up. And the scaling up is typically done using the non-dimensional parameters. So non-dimensional parameters do not come in the first stage. They will come, of course, but they come in the later stage of your engineering problem. Okay. So this is the paper that I'm suggesting you guys to read. If you're interested in conjugated heat transfer, go through this paper. Very nice paper. They have compared the radiative Nusselt number. I think you already know by now what is a Nusselt number. I don't have to remind you all. It's a non-dimensional. You just now mentioned that. Nusselt number is the ratio of the total heat transfer to the convective heat transfer. You know this. So this Nusselt number is a very important parameter to understand. And as you can see here, understand this kind of radiative convective relations. And in this example, in this answer, in this figure, this is for the case 1 and case 3. If you remember, case 1 and case 3, one rectangular, one trapezoidal, with an aspect ratio of 1. So the same aspect ratio with an external temperature ratio of 1.33. This is slightly a mistake. This is epsilon B. I'm sorry, this is a typing mistake. Epsilon B is 0.1. That is the emissivity at the bottom surface. You see that the heat loss from the top wall is greater in the trapezoidal cavity than in the rectangular cavity for the same aspect ratio. That's very interesting. Okay, so these are the results for the isotherms. For the let me quickly check my notes because I just printed it yesterday. Yeah, this is also the first. Forgot to mention it here, guys. Apologies. So this case is for the case 1. This case is also for the case 1. So this case is for the Rayleigh's number of 10 to the power 4. This case is for the Rayleigh's number 10 to the power 5. So it's a higher Rayleigh's number. Again, I assume that you know what is a Rayleigh's number. Rayleigh, R-A-Y-L-E-I-G-H, Rayleigh's number. It is a number that characterizes heat transfer in natural convection. So you are aware of this. That below a certain critical Rayleigh's number, there is no convection does not basically occur, and the heat transfer is through radiation. You know all these drills, so I don't want to go through this again. So this is an example. This is an result from the isotherms, the heat isotherms for case 1 for the two different Rayleigh's number, and this is for the square one, and this is for the trapezoidal one for the same Rayleigh's number for 10 to the 4 and 10 to the 5. What is interesting to see here is that the isotherms are more packed along the bottom and the top walls. As you can see, they are more packed. The isotherms are more packed compared to this. And what does this mean? This means that is very important for us. What does this mean physically? It means that there's a higher temperature gradient in that region, resulting in significant heat transfer that is happening. So this means that your design of the system will be more optimal, probably with a more trapezoidal effect than with a square effect for the cooker. That's something very interesting that came out from their study. Do look into their study for greater details. So this was their conclusion. I don't have to read you all, to read for you everything, because you have already the paper. They have done a very interesting aspect ratio study, the emissivity study, the external temperature ratio study. This is beyond the scope of this presentation, but please go through this paper yourself to understand what are the changes and you have done. And for me, this is a classic paper to approach a conjugated heat transfer. Okay, so now we are going through a little bit the last things of this conjugated heat transfer problem presentation. There are some challenges involved and some progresses has been done. Progresses has been done on the numerical techniques. I myself, I'm working on a numerical method, as I have told you before, that these analytical, pseudo-analytical is actually a numerical method, a kind of like a higher order numerical method that tries to improve the accuracy and efficiency of the solution. There is also machine learning applications that are going on. These are typically called physics-inspired neural network. You might have heard about this term quite often, and this is basically all about integrating the machine learning for optimization and prediction for the conjugated heat transfer problems. Coupling with fluid structure interaction, this is a very interesting work also. Some works are very slow work is being done on this, not much. So these are all the research gaps that are still existing. This coupling is so important in order to accurately measure that interaction that I talked about. And of course, the open source, you already are aware that you are in this workshop for this open source understanding, that the whole idea of using the widespread use of physical knowledge is by using open source platforms, in this case, OpenFOAM. What are the challenges involved? Challenges are computational complexity. Indeed, it is not that easy to the time challenge is a big challenge for computational problems. This interaction jump is a time consuming thing, so that's an issue. For that, the mitigation is efficient algorithm and some parallel computing. Phase change, I didn't talk about that. Phase change is another issue where we can use this phase change material, PCMs, and these are actually adding complexity to the whole problem. One way, this is not the only way, one way of mitigating this problem is to accurately represent the latent heat effects. FS I have already talked about. The transient heat analysis. Yeah, this is also very important because most of the time our heat transfer solutions are steady state. And actually that is not accurate. So to avoid the mistake, we need to change to time-dependent solution. And the time-dependent solutions are actually very challenging in terms of the transient. The general nature of transient, it's a very chaotic solution. You cannot understand whether you have reached your convergence or not, and these are real challenging. I myself have been facing this a lot, so I know these are big issues. One way of overcoming this time-dependent problems is actually to use some kind of higher numerical methods. Again, my solution is to come back to analytical solution. If your analytical solution gives a result and you say that yes, more or less the results are correct, then you can accept your numerical result. Otherwise, it is very difficult to accept such numerical results. Disciplinary optimization, I think I've talked about this. When you have multidisciplinary, thermal, structural, fluid, and let's not make life complicated. So these are big challenges, actually, big challenges, and these are the real challenges. When you want to study something on an industrial scale, of course, it is a multidisciplinary optimization problem. In that case, in one case, you may have thermal, structural, and fluid dynamics problems as well. Convergence issues I have already explained. So that's all, guys, from my side.
Okay. Hello, Professor. Hi. Okay. In slide number 8, you have explained about the continuity condition between the interface interaction. So my question is, like when Ts temperature of the solid is equal to temperature of fluid. Okay. What happens when the temperature of solid is more than the temperature of fluid? Example, let's take a plate of heated at 100 degrees Celsius and air is flowing at 25 degrees Celsius. So is there no interface between both of these? Because this condition is not going to satisfy, right?
No, it is not going to satisfy. So what you have to do here, this is a problem. I know, and these are very practical problems. Here, because you are going to do these numerical issues, you will be coming to these numerical issues. The one easy solution is you have to live with this jump, this temperature jump, but this is not correct. So the other solution is to actually refine your grid, as much as possible, so that
Okay.
you can touch the boundary layer. And this is one option. But this makes your problem very, very complex in terms of time. And I've been giving this. I've been mentioning this in my later slides, as you have said. So this is one problem. There is one professor from Cambridge, Liu He, I think his name. I have his paper with me because it's currently I'm working with all these things. He has been working on this interface interaction problem, and actually he sent me one paper, conjugated heat transit. It's a review paper he just recently wrote. It has been just published in last month, I think. He mentioned to me that he has discussed about this in his review paper. He's from Department of Engineering Science, Cambridge, Oxford University. Sorry, not Cambridge, Oxford. It would be nice if you could send me an email. I could send you this document.
Sure.
You can look into that. It's a serious problem. There's no doubt about it. It's a
Sure,
serious
sure.
problem.
Yeah. So another thing on this interface thing. So what if this interface between the solid and fluid also has a heat generation? Is there a solution for this?
Wait. Let me understand. The solid and the fluid.
Interface has heat generation. So we have a patch on the
Yeah.
solid that is producing
Yeah.
heat, and air is
Yeah.
flowing on this.
Yeah. So in that case, you have to model that as well, right? Otherwise, if it's a I think Harish presentation is going to be on that. He has a heat generation issue. So I guess, or if I understand correctly, are you having heat generation at the interface or where actually?
So exactly on the interface. So the solid fluid interface, the boundary
Hmm.
has a heat generation. So how will that work with this?
So what you need to do is basically take a lumped condition. You take the solid as a completely heat generating heat source unit instead of the interface. I don't know myself, to be
So
honest,
we
what else
basically we
can be
should go
done.
for volume. We should go for volume heat generation and have a interface outside that volume.
Yes,
Okay.
that is again, it's a limitation. By the way, it's a huge assumption, but yeah, unfortunately, that is the solution as of now. Indeed. Yeah,
Okay,
good
sir.
question.
Thank you.
Okay,
Sir,
okay,
so
okay.
I have tried that interface problem that he just suggested, right?
Yeah.
I have tried that. So, but
Can
that
you
requires
share your experience, please, John? That would be
yes.
great. Actually.
So in that case, then we have to look at the effusivity of the two fluids, right? And then whatever heat is being added at the interface will be shared by both the solid and the if it is
Yeah.
a heat source. So then whatever, suppose if on one side of the interface is a solid, on the other side of the interface you have liquid, right? Then that interface, whatever heat you are adding as a flux gets distributed between the solid and the liquid. And
So it
that
is equally
distribution,
distributed, or it is distributed in terms of
that
emissivity.
distribution will depend upon the effusivity. So you have to look that up. So that you have to look it up. So then you can maybe decide how much is going in, because you start your simulation from there and then you compute the flux, and then the balance should be there, right? Whatever you are supplying, kx dx, that way. And the distribution is dependent upon the properties of the fluid and the solid. So if you just work it out by considering this, I think you will be
It is
able
a kind of like a fluid structure interaction that you are suggesting now. It's a kind of like an FSI, actually. So I get your point. Have you published this work, John? Is it possible to read it? Then you can share it also with us, with me at least.
I have not published, sir, but I was modeling something.
Okay.
I was modeling something, so that is when I did this. So this is
okay.
There is one analytical work on this that is done by Siu et al. And I did that numerically. So I wrote my own code. So that time I had handled this. So this sort. So this generally they do when, say, you have an interface, you have a solid substrate over which you have a thin film heater, and then you have water above. So the heat that is generated within the heater will go to both the substrate. Yeah, that is a practical example. So that thin film that is getting heated, it will transmit heat both to the solid as well as the water. And that bifurcation, it depends upon what is the property of the solid material and the property of water. Okay.
Perfect.
So you can look that up.
Thank you for sharing this experience. This is very vital. As you know, this is an ongoing research, so nothing is finalized yet. But this interaction is a big problem for the conjugated heat transfer issues, and I have been facing this a lot. Thanks a lot, John.
Yeah.
Okay, so Madam Mukherjee, I think I will leave now.
Okay, that is not a problem, Dr. Datta. Thank you so much for this exciting session. I hope all of them have been benefited immensely, and also the interactive session was very fruitful for them.
Yes, I focused on this because it is they're all students and they all have questions, and this is important to answer them. And not every question I have an answer, so this is also
Yes,
important to learn what I do not know as well. It's a huge
exactly.
learning for me as well. Thank you guys so much. Bye bye.